Alright, so I got about halfway or 3/4 of the way through this video and realized I had a mistake in my notes, so I had to stop and go double check, which means I'm starting this video over, but I'm not going to rewrite all of this. So good news is this video should be a little shorter, and if you need to stop and write anything down, you can just hit the pause button. So our main point here is to talk about how heat is transferred. This is mostly going to lead into the greenhouse effect. And then we're going to look at purely just the greenhouse effects on potential global warming here on Earth. We're not going to look at any of the complexities from solar cycles or any of the other trends going along with the wobble in the Earth's orbit or the precession of the Earth's axis or the precession of Earth's orbit or the change in eccentricity of the Earth's orbit. None of these things are we're going to really look at. We're just going to limit it down to this one thing. But if you ever really wanted to look into this into a great deal, it would be a very good idea to look into those kind of things to see exactly how complicated of a problem this is and probably why it is still so highly debated. But anyway, the first part we're going to start is how is heat transferred? And so we have three main methods for that. We have conduction. And this is when heat is transferred from one object to another through a material. So if I have object A here that is hot, so this will be object A, and this one's hot, and then we'll have object B over here, B, that's colder. How do we transfer heat from there? Well, the first thing we could do is actually just put a hunk of material in between them, the material that then could have that thermal energy transfer through it. A would heat up this end of the material, and as it got hotter, it would heat up the molecules next to it, and then that thermal energy would just kind of cascade through on over into B, and you'd get a heat transfer. The second way is through convection, and this is through a fluid. So if you had A again and B again, and again A is hot, B is the cold one, same thing as before, you could put a fluid in between them, not just a solid, but some sort of fluid in between the two of them. And A would heat up this fluid at this end, and the little molecules here would, carry their thermal energy over, and you would again be able to get a thermal transfer of heat. This is like convection ovens where they heat up the air inside the oven, and then the air gets real hot, and then the air heats up the food. So this would be like the heating coil in the oven. This would be the air inside the oven getting heated up, and then the air would go over and hit B, which would be whatever food you were trying to cook. And then the last one would be radiation for heating. This is more like your microwave ovens or how the sun heats up. And this is where you would have A and B, and you could have a vacuum in between them. So a vacuum, and what would happen is radiation would be emitted by A, the hot one, and it would go over and be absorbed by B and heated up, and it would be a transfer of thermal energy between them. Of these three methods, one we're most interested in that has kind of the most interesting parts to it is radiation. And so the way we start with this, we start talking about something called black body radiation. And black body radiation is when you have an object that you heated up. Essentially, you give it some thermal energy, and the electrons start jumping orbitals. They change orbitals, and as they do this, they emit radiation. And specifically for a black body, a perfect black body, this would then be the thermal radiation of a perfect absorber. And that's hence the term black. As you know, the color black is absorbing all the light that hits it. That's why it looks black. And so if we had a perfect absorber that absorbed all wavelengths of light that were incident upon it, that hit it, then we would have a perfect black body. Of course, this doesn't exactly exist, so we don't have a perfect one of these. I remember the first experiment I was told about this that simulated a perfect black body or a close to near perfect black body was they took an oven, like a closed up oven that was closed everywhere except for a tiny little hole in it, and they heated this oven up on the inside. And so the idea was that any light that went into this hole would bounce around inside here and be very unlikely to ever make it back out. It would get absorbed by everything in there. And so that any light coming out of this hole, any of the photons coming out of it, would be photons that were created purely from the heat on the inside from the temperature on the inside of this. And so perfect, like do your fingers in quotes, perfect black bodies were then studied by making this nice little approximation. Now, some of the things that the amount of radiation coming off of a normal object, what it will depend on, and even a black body as well, is, at least the first two, is the temperature of the object. The higher the temperature, the more radiation will come off it. Of course, that should make sense because the higher temperature, typically the more thermal energy it will have. Second is the surface area. Of course, if you have a tiny little thing that's really hot, it's not going to emit as much radiation as a gigantic thing at that same temperature. So the surface area is going to matter. And then lastly, for non-perfect black bodies, or even for black bodies, it's this thing called emissivity. It's a material property. It's a property of the actual object itself to tell you how much it will, radiation it will emit. Now, one more thing back here, I didn't even give any examples of this. Of course, the sun is radiation. Incandescent light bulbs, where you had the little filament light bulbs, right? Where it was a little light bulb, and then inside you'd run current up, and there'd be that little curly thing, all right? And so it's a light bulb, right? So you'd have this light bulb, and what you do is run electricity through it, and it heats this little filament up, and it gets so hot that it glows, and so it starts emitting light, and that was a form of this black body radiation. The other thing you could think of, an example, is maybe like you've seen like someone heating up metal and hitting it over an anvil, that kind of thing, a blacksmith, when that gets real hot and it starts to glow, all types of this black body radiation. So let's continue on. Let's go ahead and define what this emissivity is. Emissivity, we're going to define as the ratio of power radiated by the object, so how much of this, how much radiation is coming off it, to the power that would be radiated by a perfect black body at the same temperature. So basically this is going to be a proportion that tells you how close to a perfect black body, how close to the ideal perfect situation this would be. So it's the power it radiates to what a perfect black body at the same temperature would radiate. Now think about this emissivity. This also goes why would a perfect absorber have the emissivity for it would be 1, it would be it over itself, everything else is less than that. Why would a perfect absorber make a great emitter? Well, if you think about it, for a photon, some radiation to be absorbed, there has to be an energy level difference between two orbitals, or maybe between any two orbitals of an electron in there, for it to absorb and move up to that valid energy level. So if that is there, then it also means that an electron could be in that higher orbital and drop down and emit a bit of radiation with that same energy here. So the more radiation it can absorb means the more radiation it can give off too if it's heated, because that means that those energy levels are actually present. If it can absorb a photon, if it can absorb that light, it can emit that light. If you remember back when we did the absorption and emission spectrums, where we had for the absorption spectrum we had the black lines, and if you compared that to an emission spectrum for the same substance, it would have emission lines, bright lines, at the places where the absorption lines were. So if it absorbed yellow, it would also then, if you heated it, be able to emit yellow. And that's because it all depends on these differences between these electron energy levels. So if it can absorb it, it can emit it. So those two things are very closely related, so that emissivity. So how exactly do we calculate something with this? And it comes from the Stefan Boltzmann law, and it states that the power emitted by an object is equal to its emissivity, this little e, times what is called the Stefan Boltzmann constant, which I've written the value of over here. It's 5.67 times 10 to the negative 8 watts per meter squared, Kelvin to the fourth, times the surface area, this is the surface area, times its temperature in Kelvin to the fourth power. And so this will tell you how much would be given off. Of course, If this was a perfect black body, this emissivity would equal 1 because it would radiate the same amount of radiation that a perfect black body would. So E would become 1 for a perfect black body, and so you need to keep that in mind that this would basically become 1, and it would just be rho A T to the 4th in that situation, okay? So that's our big Stefan Boltzmann equation. And so over here, we're going to move on to how would we draw this out? Well, if we looked at the intensity of the light being emitted, in other words, how much of each wavelength is being emitted, the graph looks something like this, where it goes up and has a peak, like that. And this peak is actually based on the temperature of the object. So if this is our temperature 1, right, temperature 1, and then we had a lower, do this one in, still do this in red, we'd have a lower temperature object, it would come up and its peak would shift over and down like that, and this would continue down under it. This would be the peak, and this would be for temperature 2, T2, and T2 is, oops, I'm drawing that the wrong way. T2 is less than T1, so T1 is greater than T2, and so on and so forth. If we did another one here, it would come up and it would shift over. Sorry, my peak wasn't great, but the peak would be over here, and then you could have another one, and the peak would shift, and the peak would keep shifting, right, like this. This isn't terribly great, but that would be, T1, T2, T3, T4, T5 down here, all getting lower in temperature, okay? And what would happen is it would trace out this nice little inversely proportional relationship. So if you just did it for every possible temperature, I know my drawing's not perfect, you would get this inverse relationship. And that inverse relationship is called Wien's law, Wien's displacement law. Sorry for the handwriting there. And basically, what we're saying is the wavelength maximum for all these different temperatures is inversely proportional to 1 over that temperature, which then gives you the actual law, which is that lambda max times the temperature is equal to a constant. Okay, so this is another relation you need to be able to use. You need to be able to use this. So if you were given, the temperature of one thing and its maximum, and you had to go through and find out another one, you'd have to do some proportions and use that to find out different things about the wavelength of the temperature. And be careful, of course, because if we're talking about light, they can use frequency and wavelength interchangeably, so you need to be able to, of course, use C equals F lambda to convert back and forth between the two. I think that's pretty much everything I had for this video. In the next video, we'll get into this a little more deeply.